so those are just to get you to think about some of the levers, and I'll talk about how we think that's playing out in some of our common terrestrial environments where we find carbonates, particularly those ones that are most common in the rock record in terms of what we can actually work with. So we can get carbonates out of soils, lakes, groundwater potentially, wetlands. This gives you some sense. This is just kind of a cartoon schematic of a given some generic terrestrial basin where you might have elevation as a mechanism for depleting your moisture source of heavy oxygen 18 or heavy hydrogen. We have sort of a number of rule of thumb magnitudes of how much isotopic signal we might get from some of those things. We have temperature effect both when you form the calcite and just within the water itself as you move, say, a moisture source up and over a mountain range. That contributes to this elevation effect. We have different, our sort of thermal lapse rates, how much we might expect elevation, temperature to change at elevation. So these are all little ballparks. And we can start putting together a framework, and I'll say take all of these with a little bit of grain of salt. This is kind of where we're at right now. About the directions we're likely to move as we get away from air temperature. How does clumped isotope relate to air temperature was what we'd really like to know geologically. And how do the O18 of water in these different settings, how does that relate to the O18 of precipitation, which typically speaking is also what we'd really like to be able to reconstruct in the past. So with soils, we have lots of mechanisms for enriching your soil water with O18, typically through evaporation. I'll show some examples where there are kind of conflicting pieces of that. But you can also imagine that if you substituted seasonality in here, are you getting summer water? Are you getting winter water? You can also play with driving this either to higher or lower O18 values versus, say, average annual precipitation. And we tend to see, but not always, a summer bias to the temperatures. So this is suggesting that we're often getting a summer bias to when the carbonate in soils is actually forming. Lakes, again, you can drive the O18 of lake water in either direction from its original precipitation source through different processes. So certainly depending on the mechanics of the lake, are you talking about a shallow lake? That's some of these playa lakes of the Southwest. Are you talking about big, deep lakes that see better mixing? How much of a role might evaporation play? If you're talking about an elevated catchment, you might also be seeing sort of a weighted average of your catchment. So you might get more negative O18 values from higher elevation that are also draining down and kind of integrating with rainfall that falls right at the surface. So it's going to look different than if you were just taking the O18 water right at that surface. And in a similar respect, we haven't done as much work on this. You tend to see a summertime bias in temperatures. But this will depend a lot on what type of carbonate you're actually looking at and what the lake is. Groundwater. So there are different kinds of carbonates that can form in association with groundwater sometimes, especially in the geologic record, or if you're working in one of these places that tends to have a really strong water table marker. This happens a lot for those of you working on soils in the Midwest. You reach that sort of, they call it the hard pan layer sometimes as you're digging. A lot of the farmers really hate some of that, but you'll get these where that water table sits. If it sits there for a while right at that interface where it can kind of degas, you'll get carbonates that form. Sometimes those are easy to pick out in the rock record. They'll look essentially, when you're looking at a profile somewhere, you get these really tabular sort of blobs of carbonate, and they all follow. You kind of watch them along the outcrop, and they all kind of follow along at the same stratigraphic level. You can get some of those. What people also sometimes mean is essentially carbonate cement. So you go out and you see a nice fluvial sandstone, and it's carbonate cemented. There are definitely those who will say, okay, well, that's probably river water. So I put lots of question marks on here because for one thing, in terms of the modern system, we haven't gotten, especially with respect to clumped isotope temperatures and formation, timing of carbonate formation, we haven't spent much time looking at it at all, so that area is wide open. And it's also, for me, a big caveat statement, right? Especially for those who are using carbonate cements, you don't always know whether that carbonate cement formed at the time that you think it formed in terms of the deposition of the rock you're looking at. It could be a carbonate cement that forms after you've buried that rock from deeper burial fluids. But again, we can start to parse some of those things apart and make some predictions by adding that extra dimension of clumped isotope temperatures. So again, we tend to think of this without having a lot else to guide us by saying typically your groundwater, once it's in that system, it's protected a little bit more from evaporation, so we don't tend to see the same sort of strength of signal. And you might also surmise you're a little bit deeper down. You're protected from some of the sort of seasonal variation of temperature as well. You might be getting something more like a mean annual temperature out of clumped isotope temperatures. And wetlands, I've become particularly interested in wetlands lately, and I'll talk about why in just a second. Again, possibilities of moving in either direction. As far as clumped isotopes go, you're probably going to dictate the timing of carbonate formation and thus the temperatures based a lot on if these are sort of ephemeral wetlands in particular, which is true of the ones where you get carbonate in them, the timing of when that dries out. Okay, so this is just meant as kind of a starting guideline to think about how we might interpret some of our data. If we think about soil carbonate, so this is an example from paleosols in central Utah. You can see these funny little carbonate blobs kind of sticking out. I had a field assistant once refer to this process as looking for going ugly jewel hunting once we realized what it was we were doing, digging holes and plucking soil carbonates. If we spend a little time thinking about our levers, I'm going to go North American US biased here again. We have a picture, a plot of a soil moisture map for soils within the western US. And we obviously can kind of see our strong east-west gradient going towards more arid and seasonally dry conditions as we move to the west. We look at soil temperature, another one of our levers. Here we're seeing a much stronger and not surprising north-south gradient. One thing not shown by this is sort of thinking about average annual soil temperatures, but what's the sort of seasonal range of some of those temperatures as well. And just to kind of make that point on levers, what you end up seeing then in, say, our soil order map is a nice hybrid of some of those behaviors. You can pick out some north to south gradients kind of a little bit more strongly in the East Coast. There's a lot of complexity out to the west, but you can also pick out this sort of aridity gradient kind of superimposed on distribution of soil orders. You can even see funny little, like, what's going on here in Nebraska. You zoom in on Nebraska, that particular soil order is entirely driven by the fact that it's developed at the Nebraska sand hills. So another lever we didn't talk about too much, but is just thinking about drainage control, right? So if you have a particular soil texture or grain size to it, you're going to really dictate soil moisture properties, potentially in both regional and localized ways that can be complicated. Okay, so in terms of a big theme that's come out of the modern calibration work, especially with clumped isotopes, is this concept of a seasonal bias to the timing of carbonate formation. And people have discovered that you can, this is an interesting situation. They went for an elevation gradient. And what they also got, they were going after trying to kind of look at, the original goal was to get a nice temperature gradient across an elevation that they could use to reconstruct elevation in the past. What they found, however, is that the rain patterns across that elevation gradient profoundly change. So at low elevations, your rain is kind of concentrated to summertime. So this is austral summer. Whereas at higher elevations, that pattern switches and you get most of your rainfall during the austral winter. And you can kind of see how that might set up some differences in what seasonal bias or any kind of bias you get to soil carbonate formations in those two settings. So here we were crossing this as low elevation to high elevation. Yeah, so you can't read that, but that's 2,000 meters versus, I think, 500 meters. And basically, if you don't look at the rest of the context, you're looking at temperatures that are the same almost all the way down. So you might expect that you'd end up with a nice gradient where you get warmest temperatures at low elevations, coolest temperatures at high elevations. But what they argued is, well, you're actually seeing a difference in the seasonal bias of carbonate formation because you have different timing of the actual rainfall. So their argument here is that in this case, soil moisture is the sort of dominant factor driving the timing of carbonate formation, and that's different in these two settings because the rainfall happens at different times. So if we go with the basic rule of thumb that warm, dry conditions with low soil CO2, and you can get that a lot of different ways, are going to drive that carbonate precipitation, here you would predict that you're going to dry things out kind of spring, early summer, or sorry, early winter up here. So that's going to be fall, early winter. The austral summer and winter always messes me up in this plot. And then here at higher elevations, you're going to kind of dry out at the tail end of their austral winter. And so they argue, in these higher elevation settings, you're getting a warm season bias to carbonate formation, whereas at these lower elevations, you're getting more of a sort of springtime bias, which will look essentially like mean annual temperature. And via that mechanism, you essentially wipe out from what you see in the soil carbonate perspective, or what you would see if this were a past setting, you wouldn't see any kind of elevation gradient in this data at all. So sort of on a seasonal scale, when you get rainfall is probably going to matter. You can also imagine that the pattern of precipitation on shorter time scales is going to matter. So this is a study doing a similar thing to the last study, but going across a kind of an east-west gradient here in Nebraska, from Nebraska to Wyoming. And what you notice here, and what you've probably experienced if you've spent any time in the Great Plains, Midwest, you get really episodic rainfall. So you might, especially farther out in the Midwest, you get some really, these convective storms. You'll get big rain, sort of burst of rain, and then it may dry out for a few weeks or even a month as a part of the summer before you get more rainfall. And so one argument is, if you're thinking about carbonate formation and what temperatures you might get out of a system like this, their clumped isotope temperatures showed a really strong seasonal bias. And this is also a little counterintuitive because this is the growing season out there. So that would be a time when you just think about basic soil productivity where soil CO2 levels are really high. So when the soil CO2 levels are high, you're more likely to get carbonate dissolution. It's right, just sort of like your analogous ocean acidification process. But what you can also see from these plots is that in between these drying events, so this is another site where they actually measured CO2 concentrations, you massively drop soil CO2 levels in between those precipitation events. So as the soils dry out, soil productivity drops, CO2 levels drop. So you can imagine what you might get out of a soil carbonate in the geologic past is some weird intervals, maybe in the summer, where you're getting punctuated times, individual funny little times throughout the summer, where you get sort of bursts of carbonate potentially growing in between in these sort of warm, dry times with low CO2 in between precipitation events. So